So, hello everyone. I hear the church bell ring of the major church, Michel, here in Hamburg, North Germany. Welcome everyone to the International Force 2020 meeting on Zoom. It's June 2022, and we have interesting talks today on our schedule. Our first speaker will be Klaus Schleisiek, and I know Klaus like 40 years, 35 years, and he will talk about Microcore and will introduce himself probably. Yeah, Klaus.
Yeah, hello everybody. I'm programming in Force since 1980 or 81. And I managed to always use Force in all of my projects. And eventually, when I was absolutely dismayed by the unpublished bugs in Texas Instruments DSP, that was around 1999, 2000, I thought that the FPGAs of the time had been grown big enough, namely the XC4013, to hold an entire Force processor. Before that, I have been part of two ASIC developments which had a Force processor in its heart, and so this was my third attempt in building a Force processor. And I think in the remaining, 20 years, it got to a point that I'm very happy with it. And in a certain respect, what I did with the hardware development is very similar to what Chuck experienced in developing Force in the first place. Because I used the different versions that evolved over time in all my projects since 2002, and eventually I came up with this version that I published on Git. So let's start. So Microcore is a wildly, and you will see why this claim is correct, scalable dual-stack deterministic computing engine for real-time control. How do I do it? Okay. So the basic characteristics is it is a computing engine written in VHDL to be run in FPGAs. It is a dual stack design. Well, I don't have to explain this. It has a Harvard architecture. So the program memory is absolutely a different memory than the data memory. And the instructions are all 8-bit wide. And so the program memory is 8 bits wide. And the data memory is a different story. The word width of the data memory and the stacks is freely configurable. For practical reasons, the smallest microcore you would run is probably 12 bits, because then you can address 4096 memory program locations. And the upper limit is just the limitation that the FPGA imposes on you as far as resources is concerned. Microcore has a real postfix instruction set architecture. And in that respect, I would claim that this is the very first real Force processor, because it also has the postfix mentality in its hardware. What does it mean? It just means that literal operands and addresses precede rather than follow instructions consuming them. That has a number of interesting ramifications. Microcore is a single cycle execution. It has no pipelining because I concentrated on getting the architecture right, and rather than running at the highest possible speed. Well, the speed is not bad anyways. It usually on the usual FPGAs runs at about 20 million force instructions per second. External events, there is, of course, Microcore can handle interrupts, but it also has a second input, which is the pause input, which is inherited from the transputer, and I will go into more detail later. It has multiple data and return stack areas for efficient multitasking. The program execution is absolutely deterministic. And Microcore is not only the VHDL code, but it is a complete hardware-software co-design environment and with its Force cross-compiler. And Force is actually Microcore's assembler. There is nothing below Force. So, and it has also a malleable instruction set. That means the VHDL code has been written in such a way that makes it easy to add instructions. The architecture. So that pretty much resembles the virtual machine of the Force itself. But you see the clear separation. Do you see the cursor on the screen? Hello, feedback, please.
Yes, yes, yes.
Okay, so this part sort of is the Harvard 8-bit part, and the other parts are those parts that have the width of the data stack and the data memory. And the I/O registers are memory mapped, and the most important ones that are there a priori before any application-specific I/O registers get added is the status register, which is directly connected or very closely connected to the instruction decoder, the data stack pointer, the return stack pointer, the interrupt flags, the flags, all other flags that don't generate interrupts. It has a version register. It has a debug register that connects to the host via a two-wire umbilical link, and the debug register is the register on the Microcore side that the host can send and receive instructions from. Then there is a timer that is also built closely into Microcore, and also it has a special instruction and a control register that allows you to set single bits, plus all the registers that you need for your application, like A to D and input-output register or DAC output registers. So stack versus registers, I skip that, we know the stacks. My interesting result of analyzing the situation for non-Force people is there are clear advantages of using a stack processor, and its big disadvantage is it is unfamiliar. The Harvard architecture, I talked about it. The instructions are all 8 bits wide. Data memory is independent, and Microcore has no bytes. So the data width is the cell width of a memory location, and it has no concept of bytes. In retrospect, that has been a wrong decision because it clearly is contrary to acceptability of people who are used to more classical processors. The Postfix Instruction Set. So it is the enabling technology for the configurable data widths. And what does it mean? There are 2 types of instructions in Microcore. There are the opcodes, and the opcodes always have the most significant bit set to 0. And when the most significant bit is set to 1, we have a literal instruction, and the remaining 7 bits are the literal itself or a part of a larger literal. And you can build up a sequence of literals in order to construct numbers on the top of stack to a size or to a magnitude that you need. And in order to do this, there is a literal flagged register in the status register, which says whether the previous instruction had been a literal already or not. So if we have the lit flag bit not set and the MSB of the current instruction is also not set, then we have an opcode that does not need a literal. If the literal is not set and we have a literal instruction, that means that a literal instruction follows an opcode. And the least significant 7 bits of this literal instruction are pushed on the stack and sign extended. So with one literal instruction, you cover the number range of -64 through 63. And not only is the number pushed on the stack, but the lit flag is set. So if we go to the 4th case, we have the lit flag set and we have another literal instruction. Now, what is in now the literal the literal that up to now has been pushed on the stack gets shifted 7 positions to the left, and the new literal instruction is just appended in these vacated 7 positions. So if you repeat this several times, you can build literals of any magnitude. So with 2 lit instructions in sequence, you get from -8,000 to +8,000. And with 3, you already have, well, it's easy. It's 3 times 7 is 24-bit precision. If you push another one, you have 28-bit, and so on and so on. So you can construct any number of any magnitude without changing the instruction set. This is the important thing. And this is why this technique enables a configurable data width. So, and if we have the lit flag set and there is an opcode, then we have the situation that the opcode follows a literal. And if this opcode is a no-op, then by the no-op, the lit flag is reset, and we successfully have now a literal on the top of stack. And the lit flag, and by this opcode again, it's a 0, the lit flag is reset. So it is no longer, it can no longer be, let's call it augmented in its magnitude.
Do you have to follow literals with no ops, or could that just be an opcode?
No, that could just be an opcode, and even better than that, if it is, let's say, a branch or a call instruction, then if the lit flag is still set when you do the branch, then we are branching relative. So we add the PC to the number on the stack. If the lit flag is not set and you do a branch, then it does an absolute branch to the location, to the address on the stack. So, okay. Single cycle execution just means each instruction only needs 1 active clock transition. But Microcore's instruction cycle may be several system clock periods long by way of a clock enable signal, which means you can run your design at 100 megahertz because that may be dictated by the application, but then you can execute only on every 5th or every fourth clock transition, you enable the enable signal, which means that then Microcore has its natural, it is at its peak performance of between 20 and 25 megahertz or 14 nanosecond delay. That's what the Microcore instructions take. So it can easily be integrated into environments. There is one exception to the each instruction needs one clock transition, and this is if you access the FPGA block RAMs. And the FPGA block RAMs, and I go back to the architecture picture, you see here an address register on the Prego memory. Well, that is unfortunately firmly built into the fabric of the FPGA's block RAMs. And more unfortunately, you cannot read out the address register. So in the first cycle, you have to set the address, and only in the next cycle, you can read the actual content of the memory. And this is why we sometimes need two instructions to do something, and they need to be uninterruptible. Because if I set the memory address and then get an interrupt, and the interrupt does something to the memory, then that is disaster. And to this end, there is a general mechanism in Microcore that allows you to build multiple instructions that consist of multiple instructions, which are a sequence that is not interruptible. And that, for instance, leads to a plus store instruction that cannot be interrupted. And so it can be used to synchronize interrupts and foreground tasks. External events. Microcore has two different input signals to react to external events. For one thing, there is interrupts. We all know what that is. And I just spell this out. An event did happen that was not expected by the software. But then there is the flip side of the coin, which is the pause. And that means an event did not happen that was expected by the software. Like, for instance, if you want to fetch a character from a serial of a UART. And if nothing has been sent across the UART, then you cannot fetch anything. And so we all know what to do in the circumstance. There is usually a UART has a status register, and then you can probe a bit whether a character has arrived or not. Well, in Microcore, you don't need to do that. You can just do a fetch on the UART register. And if there is no character, then a pause is raised, which in effect leads to the call of the scheduler and running a different task. And eventually you will come back to the task that experienced the pause. And at some point in time, the character will have actually arrived and the program can continue. This, by the way, is also something that I inherited from the transpooter, which, to my knowledge, is the first piece of hardware that had such a mechanism. As far as interrupts is concerned, each instruction of Microcore is self-contained, and therefore Microcore may be interrupted between any two instructions, with the exception of those that are, I call this chain, that are concatenated with each other. And all those instructions that exist are two-cycle instructions for various reasons. And it's about the pause. The pause is a mechanism that eventually allows you to do the resource management of, let's say, an A to D converter that is used by several tasks. you can do all this mutual exclusion and waiting for the conversion to be ready. You can delegate this to the hardware. And I think there is a transparency about this. So I talk about it later. The pause, oh yeah, here we go. The pause. So in a multitasking system, the pause trap allows to delegate, so to speak, the mutual exclusion of resources to the hardware. And then an 8-channel input, an ADC with an 8-channel input multiplexer can be controlled as follows. You store the channel number in the ADC. That starts the conversion. And then you just fetch the result of the conversion and store it in a variable. And ADC store will raise pause until the ADC is no longer in use. And ADC fetch will raise pause until conversion has finished. Hardware software co-design. The VHDL core for Microcore runs on a target system. The Microforce cross-compiler and debugger runs on a host PC. And it loads on top of GeForce 062, and because that is not very recent, Uli provided a Docker image for that. And it has to do with the fact that I needed to make changes to the a lot of changes to the interpreter of GeForce in order to efficiently implement the cross-compiler. And I needed to vector into words that nobody before ever thought that that would be necessary. So unfortunately, this in that respect is very hardware dependent. Then there is a two-wire umbilical link between the host and the target. An interactive force command line interface is mapped into a target. So you actually have the look and feel as if you would interactively program the force system on the target system. It has a disassembler. It has a single-step tracer, which is indispensable for stack checking, unless or until we finally have a fully functional stack checker. And both Microcore itself and the Microforce cross-compiler are based on the same architecture description file. And this is why I call this a co-design environment, because if you make a change to the architecture, not only does the VHDL code change, but also the cross-compiler changes accordingly. And to realize this, Microforce has a minimalistic VHDL interpreter that allows, it's mostly constants that have to be read by the cross-compiler. And so the minimalistic VHDL interpreter has to correctly interpret constant definitions of VHDL. Here is a picture of the total design flow. So we have the architecture description that I talked about. And on one side, it goes into the Microcore VHDL code and the application-specific interfaces. On the other side, it feeds the force cross-compiler. And so we can do two things. We have a source code, we crank it through the cross-compiler, and then we can generate VHDL code that is the VHDL code of the program memory, and use this in a VHDL simulator, and on the other side is the VHDL source code that goes into the simulator, so you can simulate Microcore executing force programs. So this is nice for development of new instructions and whatnot, or difficult interrupt situations. On the other hand, the cross-compiler can generate the binary, and the binary is loaded into the actual FPGA via the debugger. And this is also something that Uli has realized long ago. The FPGA is configured by throwing the VHDL code into the synthesizer and place and route programs. That is all standard technology. What do I mean by malleable instruction set? Microcore has 47 what I call core instruction, then 24 extended ones, which are kind of a luxury, and 5 instructions for floating point, which means that there are 42 unused opcodes for application-specific instructions. And adding a new instruction is a 3-step procedure. So first, you define a binary code for the new opcode in the architecture package.vhdl file. On this way, the binary code gets communicated to the VHDL code and to the cross compiler. As a second step, you add a when clause in the instruction decoder's case statement. And that is all that is needed in order to define the semantics of an instruction. You find this case statement in the file mucontrol.vhd. And for instance, the code for swap is when op swap, then store the current toss in the NOS in the next cycle, and store the current NOS in the toss in the next cycle. So important is here the R dot and the R in dot. So R and R in are records that contain all the internal registers, and I can assign new values to R in, which will be transferred into the into the registers, which are here the R dot ones, on the next rising clock edge. And the third step is to define a name for the new op in the file opcodes.fs to make it known to Microforce. And that's all that is needed. Instantiations. Microcore has been ported to Xilinx, Lattice, Altera, and Actel microsaming FPGAs. And in the development, I usually use a very small board with the LFXP2-8, which is not a very large FPGA, but here are some numbers. So if we have the core instruction set and the 16-bit word widths, we consume 988 slices. A slice in Lattice is 2 flip-flops and 3 or 4 input function generators. I'm not sure about 3 or 4. So we need 988, and I use up all the block RAM resources on the FPGA. So the data memory may be 6K wide and the program memory 8K. And the maximum clock of this setup is 33 megahertz. And which means in that instance, we have, so to speak, a single chip controller because there are no external RAM resources connected to the FPGA. It only runs from internal memory. So if we have the core and the extended word set, then we consume 1,199 slices, and it only runs at 30 megahertz. So if we have the core instruction set and a 27-bit word width, well, why 27 bits? At some point in time, it occurred to me that the block RAMs on the FPGAs are 9 bits wide and not 8 bits. And so why throw away the extra bit? And then you see the resource usage goes up. We only have 4K data memory because all of a sudden the data memory is 3 slices, 3 9-bit slices wide, whereas in the first case we only had 2 8-bit slices. So it's now only 4K, and the program memory always stays at that K. So core plus extended 27-bit is 1608 slices, extended and floating point and core is 1808. And if we only have the core instruction set with 32-bit, then we consume 1400 slices. And the data memory goes down to 3K. So, but as you can see, it is actually, you can set it to any data word width that is dictated by the application. And if you look at the human senses and what the maximum resolution of the human senses are, then you are fine with 24 bits. And plus, if you look at the technology, it is next to impossible to build an A to D converter, which is 24 bits. So a 20-bit architecture is what you actually usually need in order to solve your problems, and not 32-bit. And 22-bit is 24 plus 3 guard bits for rounding purposes. Additional topics. So these are topics I can speak about in the future, is the VHDL code and its structure, the Microforce cross-compiler, which is Microcore's assembler, the cooperative multitasker. That is a bit unusual. It is a cooperative multitasker as we all know it, but it also has prioritized tasks and round-robin tasks. And then I can talk about the pause mechanism and what you have to do the mutual exclusion in hardware. And what is also an interesting topic is floating point under the condition of a variable data word width. And I have some experiences and results there. Links. So Microcore is available on Git. And here is its documentation, and the documentation means there is the Microcore overview, which is basically what I have presented here now. Then there is an in-depth description of Microcore, all the Microcore instructions, an in-depth description of Microforce, and the Microcore public license, which is very similar to the BSD or LGPL licenses, which means you can use it and do with it whatever you like. But the license is special in that you are not allowed to claim that this is still the original Microcore model. So this is a right I want to reserve to myself or to any licensed institution to take care of this. That's it. Thank you for your attention. Questions?
Thank you very much. Yeah, are there any questions? So please raise your hands or just open the mic and speak.
The Microcore, what applications have you built it into that it's proven itself in?
Oh, quite a number. So the very first project I did was a seismic data logger that is used on the ocean bottom. Then a simple thing was a GPS to, there is an old standard for time synchronization, the name of which I don't remember right now. It takes a full minute to define the time, and it has long wave transmitters scattered around the world. That is a little bit outdated, but I once did a converter from GPS to this standard. The last project I have been doing was for the Merlin satellite a synchronization unit that conditions lasers to produce laser frequencies at a precision of 5 megahertz. And the application of this is that in hopefully 2025 or so, the Merlin satellite will be launched to measure the atmospheric content of CH4 of methane, right? Yes, at a precision of 150 by 150 meters by using two laser frequencies. So there are other.
I have a question.
Yeah.
So I have downloaded the microcore from the GitHub.
Yeah.
And here is a FPGA board.
There is what?
FPGA.
Yeah.
And I have a couple of other FPGA, from the latest microcontroller from the Altera, as well as from the other manufacturer, Xilinx. Can this be implemented on all of these?
Yeah, I have done that in the past. So I have written the VHDL code according to the 93 standard, because there are legacy development environments that don't allow, that have a synthesizer that doesn't support VHDL 2008. So yes, it should run, it should work. But one word of caution, you should get the latest version from GitHub, which I have uploaded only a week ago, because the version before has a really serious bug in it and wouldn't run if you only have internal memory. So get yourself the latest version.
Right.
Okay, got it.
Mm-hmm.
And once the fourth microcontroller MCU is created in the VHDL or Verilog on the FPGA.
I didn't understand your question.
I said, we have a FPGA, we have made a VHDL and implemented the core, microcore. After
Okay.
that, how we will program it with the Arduino IDE, can we be programmed?
Yeah, you connect it via, you have to set aside an input and output pin for the umbilical link, and then you have it under full control of the Microforce development environment from the host computer.
Okay, that I understand. I'm asking about the IDE, integrated development environment.
Arthur, now it's okay for you because we are 40 persons here in the meeting and everyone wants another.
I'm sorry.
Yeah. So I know Edley had a question, but Atta, you can just contact Klaus afterwards, and then you can discuss this. But Edley from Sweden, Norway. Yeah, sorry about that.
No, I was just wondering about those memory limitations. Is it possible to add memory chips and have access to them in case you need more memory?
Oh yes, there is provision for that. There is a general purpose external memory VHDL entity that is quite flexible. You can you specify how wide your word width you want is, and then you specify how wide the word width of your external memory is, and then all the rest goes automatically via this VHDL entity, because you may have to do several accesses to get the full data word width from external memory. Yeah, that is also already part of it.
Excellent, thanks.
Okay.